Okay, so now let's talk about diffusion. Let me zoom out here so you can see the page. Diffusion is, well, I don't know, let's just talk about it. Diffusion is it's a process for mass transport by atomic motion. Right? So it's any time you have a solid or well, even a gas and a liquid, right? You have some system and atoms in that system, and these atoms start to move around. And they get stirred, right? So it's a fairly straightforward process. If you start out with a system that's, say, a solid, and let's pick some different colors here. And you have some artificial divider that you create, or maybe, for example, you have two pieces of metal, like a piece of copper and a piece of nickel, and you take and you weld those two together. Say compound, we'll call compound A. And compound B. And here we have, say, an interface. Because you've taken these and you've joined them and stuck them together. If you look at the concentration profile, C versus X, you'll start out with concentration profile looks like this. And this. And then as time passes, materials tend to diffuse from regions of high concentration into regions of low. So you have a high concentration of A atoms here, and they're going to diffuse to the right, and a high concentration of B atoms here, they diffuse to the left. And that makes this concentration profile now change to something that looks like this. So some of the concentration that was up here has now moved over to this side, and some of the concentration profile that was up here has now moved over to this side. And then over time, these will then eventually become homogenized. And we talk about this as interatomic diffusion. And in the case of interatomic diffusion, it's being driven by concentration gradients. But we also have diffusion when you don't have concentration gradients, right? And in fact, self-diffusion is also fairly important. So if you have some atomic structure and you set this up with atoms in it, they're going to be stirring kind of constantly. And they're going to be rearranging themselves. And you look at it and you're not going to notice it, but at least not if all you have is pure material, but they do stir. And the important thing is that this self-diffusion impacts the diffusion of other species. So let's say it impacts the diffusion of dopants and impurities. Right? Because this self-diffusion, this is really kind of an internal stirring of the material. I don't know if that's spelled right. R-R-I-N-G, stirring. Right? So as you have this internal stirring, the more or the easier it is for a material to self-diffuse, the higher the rates are of diffusion of dopants and impurities. And in fact, in the case of the semiconductor industry, self-diffusion is something that, well, I would say in the 60s, 70s, 80s was extremely highly studied. And this was typically studied by using isotopes. So you would take isotopically pure silicon. So isotopes are, you're changing the mass. When you have these, you have different number of neutrons, so you can get different isotopes of your elements. And you'll take isotopically pure materials, and you would look at say one pure isotope, and then you put a layer of a different isotope of the same material, and you'd watch that diffuse in, and you could then measure the distribution of isotopes using a mass spectrometer. So you would take and you would ablade from the surface using sputtering, and then measure the masses coming off, and that would give you a measurement of the internal distribution of masses. And having said it was important in the 60s, 70s, 80s, it's still actually fairly important, and there are new mechanisms for atomic motion that people are still discovering and looking at in silicon. So I said that this internal self-diffusion is important. It's important because it affords the atomic mechanisms for diffusion. So let me, right? So one mechanism would be what I call a direct exchange mechanism, in which you would have, well, let's go back and open these up again, which you'd have, say, and then we'll have a different, say, a green atom there. And in order for this green atom to diffuse here to the right, what would happen is it would have to trade places with the blue atom. And what that means is that at some point, you're going to have 2, 3, 4, 1. Some structure like this. So you have some intermediate, and then ultimately you'd wind up with something like this. This is a direct exchange. But this is a relatively high energy process, right? Because if you look at it, these atoms are getting crammed in here, so there's a lot of strain in these bonds, and you've got broken bonds here as well. So this is a relatively, we'll call this high energy process, which means that it's less impactful than other processes. And what's more common is to have a vacancy-assisted exchange, or vacancy-assisted motion. Right? And in that case, we'd have, go back to, you have your structure here, and here you have a vacancy, which I'm going to draw as a dashed spot, and that means that now this impurity can move, and the vacancy can move in the opposite direction, giving you something like this. And you know from chapter 4 that there's always some equilibrium concentration of vacancies, and not only that, but most of the time you're working at non-equilibrium situations, and you have this net fraction of vacancy sites, and these are a relatively low energy process. If you look at this, there's no intermediate. Well, there is an intermediate, but you don't have a large atomic distortion. So this is say this is low energy process. It's also it depends on the concentration of vacancies. Which means it depends on the activation energy, or the it depends on the energy of formation for vacancies. But this is relatively common, especially in metals that have a closed pack structure where there's not a lot of space in between these atoms. However, sometimes you do have a lot of space between atoms, or you have a relatively large difference in atomic radii. And if you have that, you can have interstitial diffusion. Right? And this is what you have in the case of, say, carbon diffusing in iron. So the case of steel, right? You have some, let's draw our iron atoms is green, and then say we've got carbon, which is smaller, right? Because it's higher in the periodic table, it doesn't have D states, whereas iron has all those D states out there. Well, that means that this can hop between interstitial sites. So these sites between the atoms are the interstitial sites. And they give us opportunities for smaller atoms to diffuse through. And then finally, in some cases, you get kind of a mixture of the two. For example, in semiconductors again, your iron and other metals are closed packed, so there's very little space. But if you go to silicon, 75% of the lattice is open. Silicon is a very open structure, and in silicon, what you'll get is what we call a interstitial kickout mechanism. right? And in that case, you have structures that are fairly open. So I'm going to draw this. Like this. And what happens is some atom goes off its site. So now there's a vacancy here. I'll put an empty spot here. Vacancy. And now it's sitting in an interstitial site. And now it will diffuse through interstitial sites. And it will either come to a site which is vacant, or it will come to just another site and it will kick that atom out. So this atom now hops to the interstitial site. And this atom, which I guess I'm going to label this as kind of a filled in atom. It's going to hop into this site, and this new atom is now diffusing. So it's kind of on site, site to site, but there's this interstitial mechanism which allows for enhanced diffusion. So diffusion is extremely important in materials, and it's because it's well, because we're working with atoms, but it's also important because it's one of the tools that we use for processing. Right? Applications. Right, case hardening. Of steel. So basically, you have some steel part, and you've done all your processing. And of course, we represent all of our parts as squares. So and then the surface is something that we want to have especially hard. And this could be something, for example, you know, a cutting edge of a tool, or it could be, you know, the front of a tractor, or whatever it is, but something we need an extra level of hardening. And what we do is we would put some carbon up here, some graphite, we heat it up, and that allows the carbon to diffuse in, and we just diffuse into the surface. And that would then, we'd then take the carbon off, and what we'd have is we'd have a part, and the surface is going to have extra carbon and that's going to make it especially hard. So that's one application. Another application is adding dopants to semiconductors. Right? All of our little circuits, they rely on having a very precise control of dopants, and it's actually kind of tricky to do, but it's diffusion and ion implantation are the two mechanisms that we use. So basically you'd have some silicon wafer, and then you'd use some mechanism to deposit a very narrow pattern of something, for example, phosphorus or boron or what have you, on the surface. Some dopant. And then you heat it. And what you get is you get diffusion into the surface. And that will then give you Si, but now you have kind of regions in here of enhanced elements. For example, you know, phosphorus. P, B, coming into the surface. And this is one of the significant technologies used in semiconductor processing. So let's talk a little bit about the language that we use for diffusion and the mathematics. So when we talk about ion diffusion, we talk about the flux of atoms or the flux of ions. Flux of atoms, which is basically the amount of atoms that pass a given area in a given time, right? So if you want to think about it kind of as a rectangle, if you have some way to make a little window here that you can look at, you have the number of atoms per area, and that area is here. Per time, right? Which means that we use units of mole per volume per second, or we say centimeter squared per second, or mole per meter squared second, or we could even do this by mass. We could say kilogram per meter squared second, but it's always some unit of amount of atoms per area per time. We can take this flux, which we use the variable J to specify flux, and we can think about it in terms of a differential, since we have J is equal to mass by area time. Well, area is not changing, so what we're really thinking about is the amount of mass that passes in a given time. So that is equal to 1 over area dm dt. Right? So if you have this and you're thinking about the mass diffused versus time, that's typically going to be some straight line. I guess it doesn't always have to be, but in the case of steady state diffusion, it's going to be a straight line. And that slope is dm dt, right? Because the slope of the line is dm dt, then that's going to give you flux. Gives you the slope of the line. So if you have some way of measuring the amount of mass versus time. In the case of steady state diffusion, and by steady state we're saying that it's a situation that does not change in time, then we have what's called fixed first law, which governs the behavior. And that fixed first law is J is equal to minus D, then the derivative of concentration with respect to position. And this is our diffusion coefficient. This is the constant of proportionality that gives us the flux, that relates flux to the concentration gradient. So this would be some situation, for example, you have, say, a membrane or something that's separating a region with, say, high concentration and a region with low concentration. That's position. And Fick's first law tells us that the slope here is going to be constant. So this is going to be x1, x2. So the derivative of c with respect to x is just delta c by delta x, which is c2 minus c1 over x2 minus x1. If you look at the units, and again, unit analysis is something which we're going to use all the time in this class and the rest of your time at Washington State. We have flux, which is going to be mole per meter squared second. You have concentration gradient, which is going to be mole per meter cubed, right? That's concentration divided by meter, because that's distance. So that means it's going to be mole, up here, mole per meter to the fourth. And that means that in order to get a relationship, mole meter squared per second equal to something times mole per meter to the fourth, that means that we must have a diffusion coefficient with units of meter squared per second, right? Because that will let us cancel out that. Give us 2. And now we got mole per meter squared second, and they're going to be equal to each other. So length squared per second for the diffusion coefficient. The diffusion coefficient then gives us a relationship between the rates. This is also where the material science comes in, right? Because this is just a measurement of how much stuff passes, and this is a measurement of the geometry, the amount here and here, and this is where the material science is, and that also means that is where the the interesting properties come from, and in this case, it's going to be the temperature dependence. So the diffusion coefficient obeys an Arrhenius relation. And we talked about that last week, right? That an Arrhenius relationship looks something like this. D0 x negative q d over RT. So now this is our diffusion coefficient. This is our pre-exponential. This is our activation energy. So activation energy. Temperature. And this is the gas constant. And this looks a lot like what we saw last time, except for the gas constant. So what's this gas constant about? Well, let's have kind of a little aside here. Gas constants and Boltzmann coefficients are actually very similar. Let's call this K versus R. And they're related by the fact that R is going to be units of joule per mole Kelvin, and Boltzmann are energy per atom. Okay. B-O-L-T. Boltzmann versus gas constant. Right? And in the case of diffusion, we're talking about this mass diffusion, and this activation energy then, this activation energy is going to be energy, so joule per mole, right? Or some energy per mole. And that's the difference. And if you were to take this and move it down and talk just about the diffusion of a single atom, well then you could just as well convert down and talk about Boltzmann constant, but here we're going to talk about a mass transport. Now also last time I talked about the Arrhenius relation a little bit and what it means, right? Arrhenius relationships like this come about when you have an activation energy which is limiting or controlling the activity, right? And in this case, this activation energy, what this is telling us is about the energy for an atom to hop, right? So we were talking about the energy for an atom, well, for example, to hop from interstitial site to interstitial site. So you have some energy per position, and it's going to do this. And the atom will be sitting at some position, x1, move to some position x2, and in order to go from that, it's got to go over this hill, which means that the size of these hills are giving us the activation energy. And that's the physical meaning of it. What's more is that this also means that we can go back and talk about those logarithmic relationships. And we can use those again. Right? So if you measure the diffusion coefficient as a function of temperature, the temperature, you can take and plot those and you'll get something that looks like this. Natural log of D versus 1 over temperature, and you get a plot that looks like that. And now the slope, that's going to be your minus Q D over R, and your intercept is natural log of your pre-exponential. Yeah, you think those pre-exponentials are things that are really not easy to directly measure, but you can extrapolate them from a data set. So this is some set of measured data points. So let's So let's look at an example problem. Let's say, given at t equals 300 degrees C, the diffusion coefficient is equal to 7.8 times 10 to the minus 11 meters squared per second. And let's say that we know that the activation energy is 41.5 kilojoule per mole. So if you're given that, let's find the diffusion coefficient at 350 degrees C. Okay. So one thing that we need to do is we need to transform these into absolute temperatures. So that's going to be 300, it's going to be 573 K, and that's going to be 623 K. So we've got the temperature in absolute temperatures. We have excuse me, the Arrhenius relationship, which I'm going to write over here. D is equal to D0 exp negative QD over RT. But we can take that and we can take the natural log of both sides to get ln of D is equal to ln of D0 plus QD over RT, well, minus, I should say, negative QD over RT, right? And we talked about the logarithm rules last week, so you know how to, that taking the log of a product is the same as the sum of the internal components. And now we're going to use that for these. Let's call this temperature 1, diffusion coefficient 1, and let's call this temperature 2 and diffusion coefficient 2. Right, so if you have that, then we have two equations. We have ln d2 is equal to ln d0 minus qd over RT. It's one equation. And the other equation is ln d1 equals ln d0 minus qd over RT. And that's the second. So let's take the first minus the second, and that will give us natural log excuse me, of d2 minus natural log of d1, and taking the difference of 2 is the same as taking the natural log of the fraction d2 over d1. And that's because this minus natural log is the same thing as plus natural log raised to the minus 1. And if you want to talk about this in more detail, come to my office hours and we can chat about this. And then taking these two and subtracting them, the natural log of the d0, the prefactor, those are going to go away, which is great. And now we just take the difference here. Oh, sorry. There's going to be a 2 there and a 1 there, because temperature 2, temperature 1. And this is going to give us minus Q d over R 1 over T2 minus 1 over T1. So we can take that, and let me grab another piece of paper. So here's where we're at. And now this, we're going to take the exponential of to get rid of the natural log. So we get d2 over d1 is equal to exp negative qd over r 1 over t2 minus 1 over t1. And in this expression now, we know d1, we know t2, we know t1, we know r, we know qd, and we're solving for d2. So we get d2 is equal to d1 exp negative qd over r 1 over t2 minus 1 over t1. And when we substitute in all of these values, we get d2 is equal to 15.7 times 10 to the minus 11 meters squared per second. So that's, by comparison, just a little bit larger than the lower temperature one. So increasing the temperature increases the rate of diffusion slightly. And this is where we're going to stop today. On Wednesday, we are going to go on and talk about the non-steady state diffusion, which is governed by Fick's second law.